This video is going to teach you this thing called differentials, which is a kind of a neat use of derivative symbolism. So you have to be careful of the symbolism here. And Leibniz will be your friend. Sorry, Newton. In the first example, we have a sphere. So imagine this is a basketball, something like that. And the radius is 5 centimeters. Okay, our units are going to be centimeters. And this is the volume of this sphere. So the directions or the question would say, estimate the change in volume when a 5 centimeter radius sphere has its radius shortened by 1 centimeter. Now, I emphasize the word estimate because I know you could figure out the volume when it's 5 centimeters, and then figure out the volume when it's 4 centimeters, and the difference would be the change in volume. But what they're getting at here is they're starting to build the idea that's lurking behind the scenes that you can use derivatives and tangent line approximations and linear approximations to estimate a change of something. Now that's going to be lurking behind the scenes, and you don't even have to know it's happening, and you'll still be fine getting this answer. But just know that this is not what they're looking for. Your answer is not going to be exact. It's not going to be precise or precisely accurate, but it will be a good estimate. All right, so here's what we do. We say, okay, we've got a volume equation, and we want to estimate the change in volume. So change in volume implies that we're going to use a derivative. So I take that, and now I take its derivative. Now there's some thinking going on here. Why is the volume of this sphere changing? It's changing because our radius is shortening. It's shortened by 1 centimeter. So this radius shrunk from 5 to 4, giving us a new sphere. So the volume is changing because the radius is changing. This is where Leibniz's symbolism is so awesome. Change in volume per change in radius, or change in volume with respect to radius. So I have to get the context of this scenario to know that my symbolism needs to be dv/dr. And now when I take that derivative, what I have is a 4 pi r squared. That's just the power rule of that. But now here's what Leibniz says. He says, you know what? You've all taken algebra. You see my dr that's in the denominator? Multiply the left and the right by dr. By doing that, that cancels. This has nothing to cancel. And now I have a formula for change in volume. Change in volume is equal to 4 pi r squared times change in radius. So now if I take this, dv is what I'm looking for, estimate the change in volume, and I can fill in everything else because my dr represents a change in the radius, and they tell me it's shortened by 1 centimeter. I have to remember that in this case it's a negative. If it was lengthened by 1 centimeter, it would be a positive. And so now I've got an estimate of the change in volume by shortening the radius by 1 centimeter of a 5 centimeter sphere. One last thing to point out, my answer is a change in volume, so my units have to be a volume unit. To recap, you're taking the derivative, and now Leibniz's symbolism has meaning in context of the problem, dv/dr, that's definite meaning. Leibniz gives you permission to move his symbolism around, and once you've done that, you can plug in for any value that you have information about, and you get your answer. Life is good. On the next example, we're going to do differentials, but now there's going to be a reference to time, and that's a little bit more subtle. You have to kind of pick up the hints. So I'm going to pause while I arrange the new problem. All right, we have a new problem set up. Now we have a circle instead of a sphere, pi r squared, and we're going to estimate the rate of change of the area of that 10 centimeter radius circle as the radius is contracting at a rate of 1.5 centimeters per second. So what that's saying is Right now, this circle is in the midst of a contraction, meaning it's getting smaller and smaller and smaller, and this is the rate at which it's contracting. Well, there's a couple of hints here that I needed to pick up. They want me to estimate the rate of change of the area, and they're telling me that the radius is contracting at this rate, which, by the way, has a reference to time. Both of these pieces of information give me a hint that this problem is with respect to time. That makes it very different than the previous problem. In the previous problem, there was no mention of time whatsoever. Here, as soon as you catch the hint that it's with respect to time, your derivative is with respect to time, meaning this. The derivative of an a is a 1, so technically there's a 1 there. But since we've decided that this is with respect to time, then I write a dA dt. I just took the derivative of an a term with respect to time. That's very new to you, and that's very easy to miss. Most people in the beginning feel like they should just naturally write a dA dr. These hints tell me with respect to time, which tells me that. Now I'm going to do the derivative of pi r squared, which we know is 2 pi r, but this is with respect to time because I've taken the hints from the problem, so I just took the derivative of an r term with respect to time. Very tough to pick up on these two symbols, and you can write something else and be very, very happy thinking you're correct, and boom, you're done. Well, by the way, dA dt is the rate of change of area over time, and that's what they wanted, the rate of change of the area. So we were told that our radius was 10. This dr dt has meaning. It means the radius changing with respect to time, or the rate of change of the radius. They told us that was contracting at 1.5. So now when I put all this together, I can turn this into a number. Now it would be very easy to forget your units, or it would be very easy to remember units and then still screw them up. But Leibniz is your friend here. His symbolism, dA dt, is also a hint for units. dA is a volume, A or dA is an area reference. dt is a time reference. Area over time, area over time. In this case, area is measured in centimeters squared, time is measured in seconds. So what I'm basically saying here is Leibniz is whispering in your ear. You see this symbolism? It's telling you what units to use. So take his hints. All right, so you have differentials with respect to time, like we just did here, and differentials not with respect to time. When there's no time reference, remember that you can move around Newton's symbolism. When there is a time reference, then make sure you're including your derivatives with respect to time.